Hello everyone. In this exercise, we will estimate soil moisture through soil moisture index using Landsat 8 optical and thermal bands. For this, I have employed thermal optical trapezoid model which uses land surface temperature and vegetation index, that is NDVI, for calculating SMI. You can find details about this methodology in this research paper published in Remote Sensing of Environment. For calculating LST and NDVI, we need band 4, 5, and 10. So I have imported the required bands, that is surface reflectance band 5, surface reflectance band 4, and surface temperature band 10. For your information, I have used Landsat Level 2 dataset, which are atmospherically corrected and processed. Our first task will be calculating NDVI. You can see here in this handout. So for calculating NDVI, we will use raster calculator. You can find a raster calculator by searching or directly going to the arc toolbox and spatial analysis tool, then map algebra, and within the map algebra you can find the raster calculator. So I'm opening the raster calculator. The formula for NDVI calculation is band 5 minus band 4 divided by band 5 plus band 4. So I'm writing the formula here: band 5 minus band 4 divided by float band 5 plus band 4. My map algebra expression is okay. Many people have asked me, why do you write float here? Because the data set Landsat provide have digital number which are integer, not in decimal, but our NDVI values range from -1 to +1. So we need decimal values. That's why you have put here float. I am saving the file in my desired location. Don't forget to write TIFF, otherwise the calculation will not be done. There an error will pop up here during the calculation. Why do we write .tif? We have to set the data raster format. There are various types of raster format, uh, .tif, .img, which are popularly used in ERDAS Imagine. So if we don't write .tif, it will save it as a only raster dataset without any kind of extension. That's create the problem. So be careful to write .tif. So I have named the output file, and I want to clip my output to the area of interest, which is red boundary here. To do that, I will go to environment and reduce the processing extent to my AOI. At the same time, in raster analysis, I will mask it with the AOI. Okay. Now my formula is written, my output file name and folder is also designated. At the same time, I have limited my processing extent to the area of interest. Okay. So here is the NDVI map where the value is ranging from -0.092 plus 0.5. I am changing the symbology for better visualization. So these are the vegetative areas, dense vegetation area. These are the bare grounds. This is the water body. The river is also having the low NDVI value. Okay, so my NDV, our NDVI is okay done. Now we will calculate the land surface temperature. For that, we will use Landsat 8 band. This is the Landsat's surface temperature band. Landsat level 2 surface temperature band are pre-processed. It means the temperature values are given in the Kelvin, but they are in digital number. We need to extract or convert these digital number to degree kelvins. For that reason, there is a specific formula. This is the formula for calculating land surface temperature from level to Landsat level 2 surface temperature data. You can find details about these values in metadata file, where you can see here temperature multiband ST based band 10 surface temperature parameter is this value, and temperature additive band surface temperature band 10 is this. So we will uh, calculate land surface temperature again using raster calculator, where I will put the land surface temperature band 10 multiplied by this value, temperature multiband surface temperature band 10 parameter value. I'm putting it here, control B, plus 149. Okay, I'm copying it. So this is the formula I have written here. Again, I will give a name for the output file, that is lst.tif. Okay, save it. I also want to clip the land surface temperature output file to my area of interest. So for that, I will set the processing extent again to the AOI, and raster analysis will be in raster analysis we will mask it to AOI. Okay, okay. So here is the land surface temperature output, where you can see the land surface temperature value ranges from 289 to 304, which is in Kelvin. That's why they are above 273. If you want to convert them to degrees centigrade, you can subtract 273.15 in raster calculator. We will not convert them to degrees Celsius in this assignment. After calculating NDVI and land surface temperature, we need to extract the bare ground as well as dense vegetation, because this totem model use land surface temperature of bare ground as well as dense vegetation to calculate the SMI. For that reason, we will use extraction tool in spatial analyst tools and extract by attributes. And in extract by attributes, we will put the NDVI, because bare ground and uh, dense vegetation can be extracted from this NDVI. So I am putting NDVI in the input raster, and it is now asking for where clause, where you have to write the uh, script for extracting the value. For detail, you can understand this query builder in this section. It says you have to write value greater than 100 or whatever you want. You know that NDVI value ranging above 0.3 are dense vegetation. So I'm writing value greater than 0.3. Okay. So in where clause I have written value greater than 0.3. I will save it to my workspace and name it as dveg ndvi dveg dot tif. Okay. Okay. So you can see these are the areas where there are dense vegetation. So I have extracted the dense vegetation areas. Similarly, I will extract the bare surface areas. For that reason, our input raster will be NDVI, and in where clause we will write value greater than or is equal to 0 and value less than 0.2. In NDVI, values ranging from 0 to 0.2 are bare surface. That's why I have written this formula script here. Okay. And I will save it to the my destination folder ndvi bare.tif. Save it. Okay. So I also have got the NDVI of the bare surface. You can clearly see here that the bare surface NDVI, bare surface have been extracted from the NDVI area. Now, and you can also verify from the value ranging 0 to 0.2, and the for the NDVI dense vegetation, the value is ranging above 0.3. So we have extracted both the dense vegetation area as well as bare surface from the NDVI. Now what we need to do, we have to extract the land surface value for these bare surface as well as dense vegetation areas. For that reason, we will mask the land surface temperature uh, output file with these two areas by using extract by mask tool in the special analyst extraction tool bar. Extract was mask. Our input layers will be land surface temperature, and input raster or feature mask data will be the first. We will extract the LST for dense vegetation area. So this is the dense vegetation file layer I have put as mask feature mask data. Then I am saving it to the desired folder as lst.dveg.tif. lst underscore dveg.tif. Okay, save. Let's run it. So we got the LST for these surfaces, dense vegetation areas, which is ranging from 290 to 299. Similarly, we will mask the land surface temperature with the NDVI bare layer. So our input raster will be land surface temperature layer, and input raster or feature mask data will be NDVI bare, and we will save it to our desired location lst underscore bare.tif. Okay, save it. Okay. So we have extracted LST values for both dense vegetation area as well as bare surface area. Now go back to the formula, I mean equation for calculating soil moisture index, where which indicates ID plus SD into multiplied by NDVI minus LST divided by ID minus IW plus SD minus SW multiplied by NDVI. So ID refers to, as I told you, ID refers to maximum LST in bare land, IW is minimum LST in bare land, VD and VW maximum and minimum LST in dense vegetation. For that reason, I will use Excel to copy the values here. So our first is ID, which is maximum LST bare surface. So let's go to the LST bare layer and go to its properties. And in properties, you can see they are states, in symbology they are states. So I can easily copy the values. So I am copying it, Control C, and writing in the IW area. Similarly, I will extract the minimum LST. Okay, minimum LST value for bare surface and writing here, Control B. Then maximum LST for divage, minimum LST for divage. Okay, I'm closing this. Now going to properties of the LST divage layer, and this is the maximum LST for divage. I'm writing it, copying it and pasting it here. Minimum LST, Control C copy and Control V paste. Okay, then SD is equal to ID minus VD. Okay, similarly SW is equal to IW minus VW. IW minus VW. Enter. So we have got all the values required for our calculation. I'm zooming it. Okay. Now we will go to raster calculator and write down the formula for SMI. The formula for SMI is equal to, you have to write like this, ID plus SW. So ID value is 304.769. Control C, ID plus SD. ID plus SD multiplied by NDVI minus LST, right? Let's see. ID plus SD multiplied by NDVI minus LST divided by ID minus IW. ID, Control C, Control V minus IW, Control C, Control V, ID minus IW plus ID minus IW plus SD minus SW. Okay, SD value, SD, Control C, Control V, SD minus SW, then multiplied by NDVI, multiplied by NDVI, bracket close. So our map algebra expression is okay, and I will save it to the destination folder as smi.pif. Okay. For your information, the SW value will be negative, and as it is in negative values, we have to put it within the bracket. Otherwise, the results, there might be some error with the results. Okay. So this is the formula I have written. Now I'm clicking on OK. Here is the soil moisture index we have calculated for this study. The moisture is higher in these areas, and you can find that the dense vegetation areas have higher soil moisture. Okay, and this is a water body. Okay, I hope you understood the step-by-step techniques for calculating soil moisture index. For any kind of confusion or any kind of queries, you can contact me. For similar kind of GIS techniques and tools, you can subscribe my channel and directly write to me in my email address. Thank you.